I've chopped onto a new video because it was just getting a little bit too long on the others, particularly with how many questions there are. So carrying on, state a similarity and a difference between distance and displacement. Okie dokie. So we can say a similarity is they're both measured in meters. Both measured in meters. Difference is that distance is a scalar and displacement is a vector. So that's fine. And you want us to state something, so there's nothing more to say. We've got a couple of airports at A and C. Aircraft flies due north from A for 360 kilometers up to B. Right, so it's done 360 up to there. All right, okay. The land is what looks like the sea on this picture. I was going to say they put the airports in the middle of the sea, but yeah, the dotted stuff is over the sea then. So yeah, it's gone 360 kilometers up to there. Average speed at 170 meters per second. At B, the aircraft is forced to change course, and then it arrives at C, which is 100 kilometers. Okay, so we've got some distances there. Calculate the time of the journey from A to B. Right, so the time of the journey, so we're going to want to do the distance divided by the velocity. So what was the distance? It was 360,000, another zero. Yeah, 360 kilometers. And it's done that, so that's in meters now, and it's done that at 170 meters per second. So get rid of those. And what have we got now? So yeah, I'm putting in 360,000 divided by 17. So that is 2118 seconds. Let's just do a bit of a sanity check on that. So if we divide it by 60, so it's only taken us like 35 minutes. So that seems fine. And then what are we doing? So that's done that bit. Draw a labeled displacement vector triangle below. Use it to determine the magnitude of the displacement of the aircraft at C from A. Okay, so they just want us to do that and say, well, we've got 360 kilometers, 100 kilometers. So we just need to work out on this. If we've got 360 squared plus 100 squared, and then take the square root of that, we've got 373.6, so 374 kilometers from A to C. Okie dokie. Figure 2.1 shows a graph of velocity against time for an object traveling in a straight line. Object has a constant acceleration, yeah. In a time t, its velocity increases from u to v, yes. Describe how the graph can be used to determine the acceleration and displacement. Okay, right, they haven't been as precise as I would have liked here, but that is equal to the gradient. The acceleration is the gradient. So we're going to want to have, i.e., change in y over the change in x. So this is our v equals u plus at. So acceleration equals that. And the displacement is the area. I mean, it says displacement, but you've got a displacement from where. So this is the displacement from where it started, is all of this. So that is the average velocity. So the change in the displacement is the average velocity times the time. So v plus u over 2, so half v plus u, that's our average velocity, multiplied by the time. So the change in the displacement is the accumulation of the velocity. Use the graph to show that the displacement s of the object is given by this particular equation. Again, they're sticking with this idea that it's displacement from where we started. I mean, unless I've missed that somewhere, I don't think they've actually said it. So we've got that s is equal to a half of v plus u multiplied by t, they've got rid of v on all of this. So this one is giving us that v equals u plus at. So that's these two equations, and then we're just subbing one into the other. So we've got s is equal to a half of 2u plus at multiplied by t, which is ut plus a half at squared. So that's all pretty straightforward. So we've done all of those. In order to estimate the acceleration g of freefall, a student drops a large stone from a tall building. Okay, the height of the building is 32 meters. Time taken is that. Use this information to determine the acceleration of freefall. Right, we've already done this quite a few times. So we can assume that he's dropped it without any kind of velocity. So we've got u is equal to 0. So we've got 32 is equal to a half g multiplied by 2.8 squared. So g is going to be equal to 64 divided by 2.8 squared, which is, so 64 divided by 2.8 squared is 8.16. Right, so that's not the greatest. So it's meters per second squared. It's not the greatest thing he's ever calculated in his time. One possible reason why the answer to C is smaller than the accepted value is the reaction time of the student. State another reason why the answer is smaller than 9.81 meters per second. Right, so we need to look at the things that could have gone wrong in all of this, things that might have changed. So we could say, let's look at the other variables in all of this. So they've already taken in this reaction time thing. So let's look at some of the others. Maybe it had a starting velocity. Let's go with that maybe. So if u was not equal to 0, that could be something. So he's giving it a bit of a push as it's gone off of there. So in which case, which way would he have to go in order for that to make a difference? So he's got that it's a lower acceleration here. You need a lower value of g, so that would fit. If you've sort of thrown the object downwards, you don't need as much acceleration in order to cover the distance in the same amount of time. So that could certainly be the case. All right, next up, we've got speed is a scalar quantity, vector velocity is a vector quantity, state one difference and one similarity between speed and velocity. Okay, well, we can say they're both, this is very much what we had in the last one, but so they're both meters per second, but velocity has direction. Whereas speed just has a magnitude, so direction plus magnitude, whereas speed is just magnitude. 2.1 shows a toy locomotive on a circular track. Yep. Locomotive travels at constant speed round the track in a clockwise direction. It takes 12 seconds to go round the track. So it starts at point A. Calculate the speed of the locomotive. Okay, so the speed is, so it's going at a constant speed. That's what I was just checking there. So that's distance over time. So that's going to be 2 pi times 0.6 divided by 12, which is our time. So let's put all of that in. We've got 1.2 times pi divided by 12 is 0.3 meters per second. Calculate the magnitude of the displacement S of the locomotive from point A after it has travelled 1/4 of the way around the track. Right, so it's gone 1/4 of the way around the track. So it's got up to here. So we want the magnitude of the displacement. So we want that distance there. So yeah, we've got a right angled triangle because it's a quarter of the way round. So the magnitude of the displacement is going to be equal to the square root of 0.6 squared plus 0.6 squared. So that's 0.36 times 2, 0.72. So square root of 0.72 is equal to 0.85. 0.85 meters. Explain why the average velocity of the locomotive is 0 after a time of 12 seconds. Okay, right. So the average velocity is the rate of change of displacement. But the average, the velocity is the rate of change of displacement. The average velocity, we can change those into deltas, delta S over delta T. So at t equals 12 seconds, delta S is equal to 0. Therefore, the average velocity equals 0. I mean, you could just say on that, well, the displacement hasn't changed. It's got back to where it started. It's returned to A, that sort of thing. Explain why the velocity of the locomotive changes even though its speed is constant. So that we can have because direction of motion is changing, because this comes back to what we said at the beginning as one of the differences between velocity and speed, that velocity includes direction. So yeah, that's quite a nice one. Define acceleration. So acceleration is the rate of change of velocity. So we've got dv dt. If you're going to write dv dt, well, still say what it is because they're going to want to know what these v's and t's are. So you might as well just write out rate of change of velocity. State 2 factors that affect the acceleration of an object. Okay, Newton's second law are telling us that force over mass is acceleration. So there we go. We've got the force, we've got the mass. So the force applied to the object and the mass of that object. That's going to be 2 factors in play there. Figure 4.1 shows the variation of velocity v with time t for a small rocket. Okay, so zipping up in the air, coming back down again by the look of it. The rocket is initially at rest, fired vertically upwards from the ground. All the rocket fuel is burnt after 5 seconds. So that's where we've reached our peak velocity of 200 meters per second. Assume that air resistance has a negligible effect on the motion of the rocket. Without doing any calculations, describe the rocket from t equals 0 to t equals 5 seconds. Okay, so we've got a positive velocity and we've got a positive constant acceleration. We don't want to do any calculations. I mean, there isn't really too much more to say apart from that. Positive velocity going from 0 to a maximum, but and then from t equals 5 to t equals 25. Okay, so we've still got positive velocity and we've got a negative constant acceleration. So that seems to be the bits of interest there. Calculate the maximum height reached by the rocket. Well, I've used this question before in the past, and people tend to make, if they're going to make a mistake on this, they make the same one as they work out this area here, up to the maximum velocity. But of course, the maximum height is going to be all the way up to 25 seconds. It's still going upwards. This is all positive velocity. So we want the full area of all of this is going to be the maximum height. So our maximum height is going to be, for one of these triangles, we've got 5 times 100. And the other one is we've got 20 times 100. So what am I doing? 20 times what? I'll just do it as one lump. So we've got 500 and 2,000. So we've got 2,500 meters. So yes, don't forget to include all of that area. Explain why the rocket has a speed greater than 200 meters per second as it hits the ground. Right, okay. So it's got to 200 meters per second at some after 5 seconds, but that's not the maximum point. So the when we get up to the maximum height of 2,500 meters, and then we drop from 2,500 meters, well, it's going to be going faster than it was when we were this amount of, this amount off of the ground. I don't think I made that for particularly clear. But still, we're saying conservation of energy. Conservation of energy. Let's write it out this way rather than my waffling that I just did. So conservation of energy, we've got mgh equals half mv squared. That's what's happening there. So get rid of those. So our v is equal to the square root of 2gh. H we know is 2,500. So v is the square root of 5,000 g, which is, well, it's going to be more than 200. So let's put all of this in. We've got 5,000 multiplied by 9.81 equals that. The square root of that is equal to 221. So that's 221 meters per second. So you could put it at that. I mean, you could say here maybe when it's got, so at v equals 200 meters per second, rocket also has GPE. That's where it's coming from. You see, it's easy to forget about that gravitational potential energy at that point. And then that has to go into kinetic energy. So you can either do the calculation, or you can just say this, that you've got that kinetic energy plus some GPE, and that GPE is then added in to create an even greater kinetic energy. So, a couple of different ways of describing the same thing, whether you want to go down the formula route, which is probably easier and safer, or whether you actually want to write out some words. And when you're practicing, it's nice to do both, because it's nice to give these explanations, saying, when it's traveling at 200 meters per second, it's got that corresponding amount of kinetic energy, but it also has gravitational potential energy. When it hits the ground, that gravitational potential energy is added to the kinetic energy, in which case you've got a higher velocity, or at least a higher magnitude, greater speed on that velocity.